Hello, my name is Todd Rothman, and I want to welcome you back to Organic Chemistry 1. In this video, we're going to go over how to draw Lewis structures. Now, up to this point, we've learned all about atoms. We understand how to put electrons around the atom. We understand how to determine the charge, the formal charge of an atom. And now it's time to start to learn how to connect atoms together. So what we're going to do is there's a few different ways that we can draw on paper the connections of molecules or atoms connecting together to make molecules. But what we're going to do to begin is the most classical way of drawing, and that is what's called Lewis drawings or Lewis structures. Okay, so this video is going to be broken up into two parts. The first one is just going to be a bunch of rules that we have to remember while we approach drawing structures, Lewis structures. The second part of this video is going to be where we practice, I think it's 6 or 7 problems together. And after you're done with that practice, you will have a good understanding on how to draw Lewis structures. Okay? So let's get started. Let's talk about the general introduction of this topic. Now, Lewis structures have been around for a very, very long time now, and people have used this to illustrate molecules and the connections between them. What's important to note, but this applies not just in Lewis structures, but in any drawing that you do on paper, is that we're always focusing in on the valence electrons. See, remember, the valence electrons are the electrons that are furthest from the nucleus. They're the ones that engage in reactions. They're the electrons that get transferred to other atoms or share electrons with other atoms in order to make bonds. So it's always the valence electrons that we're most concerned with. Okay, those are the ones that have the weakest attraction to the nucleus, and they're the most accessible, and they're if you think about it, they're the first line of defense when another atom comes close to it. So they're the ones that interact with our other atoms. So Lewis drawing is all about first identifying the valence electrons for each atom that you're dealing with. Okay, now we're going to use a line to show connection between atoms, and we're going to use dots to show lone pairs or non-bonding electrons. That could be either a lone pair or it could be a single dot, which is actually called a radical. Okay, so we're going to use dots on for electrons that are non-bonding and lines for connections between two atoms, bonds between atoms. Now, before we go on and talk about how to draw Lewis structures, we have to just identify with some common trends, okay? And these trends, it's not an exhaustive list, and this is just trends that you see over and over for our focus in organic chemistry, okay? So this is like kind of honing in on things related to organic chemistry, atoms that we deal with on a daily basis. All right, now the first thing is the trend of just knowing what it means to have a filled outer shell. And we've touched on this already in the video about valence electrons, and we also touched on it when we talked about formal charge. So again, we're back to that, and this is a very important thing. We're going to see it over and over. So we have to know how many electrons are in the outer shell of certain atoms. Now, hydrogen, for example, is an exception to the octet rule, right? It has only an s orbital, 1s, which means its maximum number of electrons are in its outer shell is 2. So it makes one bond. 2 electrons per one bond, right? Remember, each bond represents 2 electrons. So hydrogen wants to make one bond. Boron is a group 3, so that means it has 3 valence electrons. And to make covalent bonds, that means it can make 3 on its own. Each one electron can join with another atom's electron, right? 3 times. So boron, traditionally, it will make 3 bonds. Now, it could make a 4th bond, and we should keep that in mind, but it doesn't normally do it on its own. There's a chapter that we'll talk about for the next exam, chapter 3, acid-base chemistry, in which we'll learn all about how boron acts as what's called an acid. And we're not going to learn about that now, but we'll see it later. Okay, but realize that boron can make a 4th bond. We should just be familiar with that. And if it does make a 4th bond, it becomes negative, okay? And that's something that you could figure out by formal charge. All right, nitrogen. Nitrogen likes to make 3 bonds, but it can make a 4th bond. And so you have to keep that in mind. So your first approximation is to make, your first guess would be to make 3 bonds from a nitrogen. But if you see that you have to add another bond somewhere or something's not working in your drawing, you should keep in mind that nitrogen can make a fourth bond. Oxygen likes to make two bonds. That's traditionally what it does, like H2O, for example, but it can make three bonds. And again, it's something that you don't jump to during your first attempt drawing a structure, but you just know that that exists. You have to keep that in mind. Now, phosphorus and sulfur are the ones that can go beyond 8 electrons in its outer shell. Remember, phosphorus and sulfur are third period elements, which means that they have d orbitals. So they could make more than 4 bonds. They can have more than 8 electrons around them. They can make 5 bonds and 6 bonds and so on. So here's the rule. Phosphorus is right underneath nitrogen, so it can make 3 bonds just like nitrogen. It's the same group 5 element. So it can make 3 bonds, but it can go up to 5. So 3, 4, or 5. Sulfur is right below oxygen. It's a group 6 element. So it can make 2 bonds. That would give it 8 electrons, but it could also make 3, 4, 5, or 6 bonds. So this can make 2 to 6 bonds. These are the trends that you need to keep in mind, and we're going to see this in practice in the next section, okay? So, but this is what you want to keep in mind. You'll have this on your note or you put it to memory, however you want to do it. These are very important trends to remember. Okay. The next trend that we're going to keep in mind is that when you're dealing with oxygen or halogen, you don't want to initially bind them together, okay? Let me show you why. If you have an oxygen, let's say with an H on it, and you connect it to another oxygen that has an H on it, the problem with this bond, this is called a peroxide or a proxy bond. And the issue here is that both oxygens have lone pairs twice. So the bond between them is connecting them together at a closer distance. The issue here is that the lone pairs on these oxygens are also coming close together, and they're going to start repelling each other. So we're creating what's known as potential energy in the system. These oxygens are getting too close together, and so the electron pairs around them start to push them away, and it makes it an unstable connection between them. So these type of bonds generally we don't see. Now, let me make that clear. I shouldn't say that. Peroxides exist in nature. We'll learn about them, but we wouldn't start by drawing them together like this, okay? We always try to put them separate from each other. The same thing, let's say, with a halogen. If I have a Cl and I connect it to another Cl and then let's say a carbon, first off, halogens only want to make one bond because they're like they have 7 electrons around them. One more gives it a filled shell. So to put a halogen with 2 bonds is very unlikely. So this tends to not happen. It could happen, but generally speaking, you probably wouldn't start this way and you'd be correct. All right, and it's very much for the same reason as oxygen. Halogens have 3 lone pairs. So there's a lone pair here, 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 and this one has 2 lone pairs. So there's a lot of repulsion between them, right? So not only do halogens not connect, but oxygen and halogens don't connect. So if you have a Cl and an O, there are a lot of electrons around these 2 atoms, right? And so there's a lot of repulsion going on. So you don't want to do that. This is very unlikely to take place as your initial approximation, okay? Again, if you find that you'll see when, but in our case, we're never going to draw that connection. But if you're kind of working your drawing, you're not getting it right, then maybe you would try that. Otherwise, you try to avoid doing this, okay? These are things that you avoid. All right. The next thing is avoid making radicals. Now, what do I mean? If you have, let's say, a carbon, and you want to give it electrons, non-bonding electrons, meaning they're not shared with any other atom, then the chances are give it a pair before you go ahead and give it one. Don't break electrons up. Don't split them up. So like give carbon 1 and then the neighbor atom 1. Try to give one of those 2 atoms 2 instead. That's the point of this. Now again, radicals exist. So it might be that you're dealing with a radical, but that wouldn't be your first guess. Okay, this is all about trends that you typically find. And so drawing a radical